Let's dive deep into the world of electric fields, one of the most elegant and powerful concepts in physics. Whether you're preparing for a test or just want to truly get how charged particles interact by the end of this video, you'll have a solid and intuitive grasp on the topic. Let's begin from the basics and build up to more complex stuff, step by step. But before we dive in, there's something kind of wild that's worth sitting in for a bit of a second. We talk about forces, gravity, electromagnetism, even the strong and weak forces. It's like they're just normal parts of physics, but conceptually, they're a bit strange. I mean, what actually is a force that acts at a distance? Like, why does a charged particle sitting alone in space somehow just know that another one exists a few centimeters away and decides to move? No one's physically pushing it, there's no string connecting them. It's like a bit of a silent conversation between particles across space, with no visible messenger, just pure influence. This goes even deeper. Think about this. Why do objects feel solid? You can't, push your hand through a table. You're not really touching anything in the traditional sense. Actually, the electromagnetic forces between the electrons in your hand and the table repelling each other. So, I mean, is this the sensation of touch just your atoms refusing to overlap? It's quite weird because atoms themselves are mostly empty space. Okay, I'm getting off track here. This video won't try to answer any of those questions. But I want to acknowledge that at its core, physics doesn't always explain why the universe is like this. It's just how it works, rather than why. And sometimes that's alright. Sometimes it's strange enough. First are the properties of electric fields and the impact on particles. Electric fields only interact with charge. Other properties have nothing to do with electrical fields. That needs to be very clear. That mass, size, pretty much anything else has nothing to do with electrical fields. Electrical fields care about electrical charge. An electric field can pervade any kind of space or environment, and charged particles move within these fields because there's a force on them. Force is sort of the fundamental idea of interaction between things. So not nothing, not the environment, but things. And this is for any and every case in physics. The first equation we will encounter is the intensity of an electric field, and this can be calculated as the force on some particle over the charge of that particle. And for reasons we'll go over in a second, that's also equal to Coulomb's constant, denoted K, multiplied by the charge of the electrical field all over the distance squared. I also want to just establish that an electrical field's a bit of an imaginary thing. It's sort of the extent that something electrically charged tries to interact with the environment. It is quite powerful, and like all forces, has infinite range. Things that are also charged inside this field will be influenced in some way by the force we mentioned before. And this causes things to move and do weird things that simply exist unimpeded or unmoved. And this comes back to the idea that things are sort of born with potential. So I guess when the universe was created or something like that, all the potential energy in the universe already existed. So when something's far away, it has the potential to be attracted, possibly if they're opposite signs. And it's not just creating energy out of thin air with this force. I need to emphasize that this force it has a source. I also want to establish that a force is very different from motion. Force will always be equal in these circumstances since force only cares about charge. And if charge is the only variable, then that's literally it. Motion will, however, be subject to other things. For example, acceleration as an idea of motion is equal to the force over the mass, because F equals ma, as Newton taught you all those years ago, and so A equals F over m. And while we can calculate the force, which will just be about charge, then we also have another variable, mass. So a bigger particle with a same charge will obviously move slower than a smaller particle. And a good rule of thumb, not even just for electromagnetism but in general, is to look at the relative equation that tells you about these concepts. If the property is a variable in the equation, then it matters to understanding how the thing will behave. If it isn't in the equation, it doesn't matter. Let's look at kinetic energy. Half mv squared. So I can tell straight off the bat that kinetic energy will only be determined by the mass and the velocity. It doesn't care about charge. Now, by proxy, the velocity might care about charge, and if the kinetic energy cares about velocity and velocity cares about charge, then the charge might influence it, but that's influencing kinetic energy not directly, but through velocity, by changing velocity, which will then, as a result, change kinetic energy. Something else to establish is that fields can be scalar, vector, or tensor, but in electrical fields, they're vectors. So each sort of spot on this field that exists in the environment has some magnitude and direction. And with one charged thing, the field is absolute, and it can be understood and equated perfectly. And this is like a point charge, we can understand its electrical field completely. When there's multiple charged things in the environment, their individual fields interact and build up or cancel out each other, depending on the properties of each item in this system. Something else I want to touch on is the idea of systems. Now, physicists use the word system quite a bit, and it was never really properly explained to me, and it took me quite a while to actually really understand this concept, that the system is only used in the context of theoretical calculations. So the system's like the environment. It's everything. It's what we're looking at. It's what we're analyzing. It's things inside the environment, assuming nothing exists beyond this imaginary box, this imaginary enclosed environment that has all the things accounted for. And this is just to simplify theoretical explanations. So if I had a box on Earth, then that's not an isolated system by itself, because gravity outside the box is going to be also affecting the items inside. The universe is an isolated system. An isolated system essentially has no external factors. It's like everything happening in the box universe. Outside the box is like outside the bounds of the universe. It's sort of the idea of nothing, but you can't even call it nothing, because then we're calling it, then it's something which is nothing, and then you go cross-eyed, and there's no point in pursuing that any further. But for theoretical whiteboard calculations, an isolated system is not affected whatsoever, except with what's in it and the environment in which contains it. While it may seem trivial, any good high school physics teacher should make you draw some field lines that represent certain electrical fields, given point charges, plates, and other oddities. So we'll have a little look at 4 cases, with being 1 point charge, 2 opposing point charges, 2 parallel plates, as well as a hollow conductor. These are probably the big 4, and probably the only ones you will encounter should you do a test. So the first in this circumstance is a single point charge. For all of these diagrams, the grey lines will represent the field lines, and any coloured item will either be red for positive or blue for negative, and these represent the actual things that are charged in the environment. So for any singular point charge, the electrical field lines radiate out in all directions in straight lines. And we also draw arrows on each of these radiating field lines to sort of represent the charge direction, and it always goes from positive to negative. Very simple case. If the thing in the middle was blue and it was negative instead, then all the arrows would be pointing inwards. The next circumstance is 2 opposing point charges. Now around the back they are barely affected, so they pretty much just have straight lines radiating out once again. However, in between them, the electrical field distinctly travels from the positive to the negative in ever increasing curved bands, as so. 2D parallel plates, assuming that these plates extend indefinitely, have completely straight field lines directly from the positive plate to the negative plate, or the higher voltage plate to the lower voltage plate. The distance in between them affects the intensity of this electric field, as well as the difference in voltage. However, the field is completely uniform throughout, so if I was a particle sitting anywhere in the middle of these 2 plates, I would always experience the exact same electrical field. And the intensity of this electrical field, contrary to the regular equation used for intensity, can be described as E is equal to the difference in voltage over the distance. The final example is a hollow conductor. Just pretend this thing in the middle here is not 2-dimensional and is a sphere. So it's a sphere that's empty on the inside. Now if this was charged, the field lines radiate outwards in exact same fashion as the point charge. However, the interior of this conductor is completely neutral, and this can be very useful to cancel out other electrical fields and can be used for protective purposes in certain applications. So your teacher should ask you to draw these ones, and it's good to just remember them for the circumstances that any of the problems ever arise. You can sort of conceptualize it before doing all the maths and the equations or whatever. But that's all I wanted to say in terms of drawing and visualizing these diagrams. So the first very important equation, I guess they're all important, but this one is very good to remember because I'm sure there'll be work problems about it. You know, this was basically just all the work problems I got in high school physics, is Coulomb's law, which is a way to calculate the force between charges. So like how Newton's gravity equation is the gravitational constant multiplied by the first mass multiplied by the second mass all over the square of the distance between them. The electricity equation is basically the same thing. It's another constant, but this time Coulomb's constant, multiplied by the magnitude of the first charge, multiply the magnitude of the second charge, all over the square of the distance. And they're both forces, basically the same equation, and actually that comes up later that if you're trying to figure out, when the gravity equation is equal to the electricity equation, then nothing's moving because one's pulling this way, one's pulling that way, and it gets quite logical and conceptual rather than mathematical. And you can basically just use a calculator to input these values and figure out stuff if you want. And as they're constants, I just wanted to touch on them that Coulomb's constant is 9 times 10 to the 9, and the gravitational constant is 6.7 times 10 to the negative 11. So this actually shows as well, it's a good point that electrical charge is a lot stronger than gravity. Gravity's very weak. It is the weakest force. It's weaker than the weak force. I don't know why we called the weak force and gravity if gravity is the weakest force. But gravity, it kind of sucks. It doesn't peter away as much though. So for example, the strong force is the strongest force, but only at very close distances. And that goes into a whole other can of worms that we're not going to go over today, that certain particles that have like charges can actually be attracted to each other through the strong force because the strong force overwhelms the electromagnetic force, but we don't care about that today. We're doing high school here, not university. You might also ask why. How is it that so conveniently these two equations are pretty much the same? Well, as humans, we made it so. We made it so our units would line up perfectly for these purposes. We made concessions in our units. We gave them weird numbers like 6.7, 9 times 10 to the 9, like charge, and so this would work. It's like Avogadro's number in chemistry. The reason that the mole, the number of atoms in a mole, is the perfect number of atoms so that the mass of that sample in grams is equal to the number of atomic mass units in an individual atom that makes up that sample, is just because we've assigned the number of atoms in that mole to 6.022 times 10 to the 23rd or something like that, and that's just because we've made a concession in some other front to work that out. And the same with these constants I've established, and also they have pretty disgusting units because the force is in newtons. We have all these other units that we're using in the equations like charge twice, and then we've got like per distance squared kind of thing, and there's no even mention of any newtons. So in order to cancel out the distance on the bottom, it has to be Newton meters squared and then over whatever the other things are. That's just a property of these kind of equations, that we need to equate the units as well as equating the variables. Now, using this equation, it can be used to calculate the force between two point charges in one system. The force on either one is always the same, and they feel the same force, but it just depends on whether it's attractive or repulsive depending on the charges. But that works itself out, because for Q1 and Q2 you would assign, +2 or -3 depending on if it was a positive or negative charge. And this actually also raises another good point, that something unique to electromagnetism is the different facets of how the force can be expressed. So it can be a positive or negative force. It's not just an absolute force. Like gravity, it's just an absolute force. It only attracts. Whereas electromagnetism can attract or repel depending on if it's positive or negative. This is one of the great mysteries of the universe, and this goes back to a whole other can of worms that we're not even going to try to explain, because if I'm being 100% honest, I've got no idea. And I don't think anyone else really does either. There's theories, but there's no absolute. Maybe one day, if you want to see a video like that, we can discuss what's going on there. So now we've got the intensities of all the charges, the intensity of the field, but what can we use this information for? We can calculate movement, and movement's something quite fundamental to the universe and something that charges significantly affect, and it's good to understand how that works. So we know that the field is equal to the force over a point charge, but given that the force is equal to Coulomb's constant multiplied by the charge of the electric field all over the distance squared, we could say this is also equal to the point charge multiplied by the intensity of the electric field. However, we also know the force is equal to the mass times acceleration from Newton again. So therefore we can equate both sides because they're both equal force. Mass times acceleration is equal to point charge multiplied by the intensity of the electric field. So the acceleration is equal to the point charge multiplied by the intensity of the electric field all over the mass. How is this helpful? Knowing the charge of some thing inside this electrical field that can be calculated as an individual field or a net of multiple fields, as well as the mass of the item, we can figure out its acceleration at any given sort of point in this electrical field. And this has a direction and a magnitude, also known as the rate at which the acceleration is happening. Knowing the charges, we know everything about the system and how it will move as time progresses in this environment. Any movement also has kinetic energy, a fundamental part of the universe. And the energy equation in this circumstance is equal to the charge multiplied by the change in voltage. Now, when something's moving through a field, it doesn't develop any energy. Like gravity, it has potential if charged and in a field, and since the field extends indefinitely, we have potential for every possible field that exists. But that's like in the actual universe. In this sort of theoretical universe, when moving through the field, the potential will change. It will convert into kinetic energy. Vice versa, if we're then sort of forcing the thing higher point electrically, so like a higher point gravity-wise, gravitational potential energy increases. Higher point electrically, it doesn't need to be a higher point. What does higher even means? Goes back to relativity. No, we do not have time. But all you need to know is that the work done by some item, the energy, is equal to its charge multiplied by the change in voltage from its starting point to its end point. That pretty much covers all the concepts in electromagnetism in high school. But there's some special cases that I want to quickly have a little look at. First of all is a charged particle in between infinitely extending 2D parallel plates. So if the force in between these parallel plates applied to some charged particle equals the force downwards of gravity, so this is in the real world again, we can suspend a charged particle in between these plates. First of all, keep in mind that the magnitude of the charge between plates is equal everywhere, so the electrical field in between these two plates is the exact same, no matter if it's a little bit closer to the top plate, a little bit closer to the bottom plate, no one cares. So wherever you essentially place this particle, if it meets the next requirement, it'll just stay there. So it doesn't need to be right in the center. It can be a little bit further up, a little bit further down, whatever you want. And we know that the gravitational field, which is the mass times acceleration due to gravity, if that is equal to the charge of the point charge multiplied by the electrical field, which is V over D, as we established before when looking at specific electrical fields, then we know that we can calculate any of these variables if unknown. So obviously, if we're always on Earth, it's always going to be the said gravitational acceleration. If we know the mass of the particle and the intensity of the electrical field, which is essentially just going to be the structure of the two plates, then we can calculate the charge of the particle we have. So we can use this to find, excess charge on a big object like a pith ball or an individual electron, and that's even easier because we know the exact mass of an electron at all times. It doesn't change. It's basically just a solve for the unknown if you ever encounter this in a test. Another cool thing to look at is how a photocopier works. Now, I've always been seriously fascinated with how photocopiers work because they always seemed quite peculiar. And actually, this is how a lot more things work that, like digital cameras, like how they capture a moment in time. Now, what is this capturing at the moment? Well, it's light. We're capturing light. So, in particular, a drum-style photocopier has a large charged piece of metal inside, and first of all we apply a uniform charge to it. Now you put the paper that you want to scan on like a glass window, and there's a moving light bar that shines across the whole thing, and as it's shining up at this paper, the white areas reflect the light, whereas the black areas absorb it. Now these photons shoot straight back down onto the metal drum that's below this light, and the reflected photons, they hit that drum in the same pattern that the ink is on the paper. And what happens is that where the photons hit, they essentially steal the charge off the drum, but only at that specific point. And this creates what is essentially a fingerprint of the ink on the page, but in terms of charge difference spread across the drum. Now a computer can then interpret these differences in charges into a digital document, and it can be printed again, it can be reprinted, can be sent online, it's whatever you want. What about grey? And this is something that sometimes at face value doesn't make much sense, but we need to emphasize that particles are quantized, and so they're either 1 or 0, they're discrete, they're either on or off, they're not half on. That doesn't really make much sense, does it? So, and because there's so many of them, their density per bit of the page is interpreted by our eyes as different shades of grey. So a crisper black will have less photons coming off of it, but fundamentally they're still just either photon or no photon. The drum's a lot more sensitive, even though our eyes can perceive an individual photon. That's like a thing that everyone knows now. It's one of those biofacts that you sort of you blurt out to sound smart, but the drum can perceive it quite well. Same with color TV. It doesn't matter that the screen can only show red, green or blue. Our eyes meld them together, and actually that's just how our eyes work anyway. They can only see red, green or blue, but they meld them together because they know in your brain, and this comes back to even a crazier idea just about how can we conceptualize just electrical signals in our brain about what we're actually seeing. What does visual even mean though? The last case study I wanted to look at was a solenoid coil. Now this is probably the best thing ever since sliced bread. It's probably even better than sliced bread. It's a charged wire or something along those lines that is wound into a cylindrical coil, and it creates a very distinct, very strong magnetic field. Now if you just got a random coil, put an electrical current through it, and it was just in some strange shape, it was like a modern art decoration, it creates a pretty weak field. But this specific formation creates a very strong and very uniform magnetic field. And it looks like this. This is used in heaps of applications like particle accelerators, it's used in transformers, used in generators, used in anything that you see people like wind copper wire around and they say, yep, this is gonna do something, this is gonna blow the enemy off the face of the earth kind of thing. That's what they're doing. Also, because it's a wire, it'll only work when electricity current is flowing through it. These are essentially magnets that we can turn on and off. This is like the most useful thing in all of history. Seriously, sliced bread just doesn't have anything on this. And there's an equation that we can use to calculate, which is mu naught multiplied by n multiplied by I over d. And you think it kind of looks like the plate equation except with a bunch of stupid letters. And you're right, I is the current, and it's I because they call it impedance in electrical and stuff, but it's current. N is the number of twists we have in this coil we've made, and mu naught is the permeability of the environment around the coil. And thankfully it's just a constant, which is 4 pi multiplied by 10 to the negative 7. What the heck's permeability though? Think about it, how some solid has conductivity, so some things conduct better than others. You know, copper conducts a lot better than wood. How well can it facilitate the electrical charge? The environment needs to facilitate the electrical field, and we've sort of found as scientists that different environments have unique abilities to facilitate the electrical field, so we termed it permeability. One final thing is the connection between electricity and magnetism. One affects the other. Magnetic fields produce electricity, which can be seen in generators. Electricity can produce magnetic fields, which we see in solenoid coils. In fact, all of these charges we've been discussing are electrical charges, but they're magnetically attracted to each other. So what's the big deal? I can't claim to know why this is. Again, universe stuff. The man upstairs got some tricks up his sleeve, and we haven't figured them out yet. But think about it like this. Science is weird and wonderful. Things we don't know yet are incredibly hard to demystify. But did that stop anyone in the past? No! We should look at these problems like how classical physicists looked at quantum physics. How could we ever see the smallest things and measure them? How could we see galaxies unfathomably distant? Maybe you will help us get there. Till next time,